In section 7.1, we'll continue to look at the case of right triangles and applications now, of course, because we're in that chapter 7. Later on, in the next two sections, we'll look at the case when our triangles are not right triangles. This box down here at the bottom is really, really important to the whole course, really. Back in chapter 5, which was about unit circle trigonometry, we defined the sine and the cosine and the other trig functions under the presumption that we had a unit hypotenuse here. In other words, that the point corresponding to the angle was on a unit circle trig. So for a unit circle, C would be 1, and then in that assumption, remember that the y-coordinate of the point on the unit circle was the sine of theta, and the x-coordinate of the point on the unit circle is the cosine of theta. Notice how that plays out in these formulas here. If we were on the unit circle, so the hypotenuse had length 1, right up here, then the sine of theta would be the opposite, which would be b, the y-coordinate. Likewise, the cosine of theta, in that special case when we're on the unit circle where c is equal to 1, the cosine of theta would be a, the x-coordinate on the unit circle. And down here, the hypotenuse again would be 1 if we're on the unit circle, so cosine of theta would be the adjacent, which is a. In the real world, not all right triangles have their hypotenuse equal to 1, so that's why we need to have these generalizations of the trig functions to those situations where the hypotenuse is something other than 1. It's really important to memorize these, that sine of theta is the opposite over the hypotenuse, so opposite b over c. Cosine of theta is the adjacent over the hypotenuse, adjacent hypotenuse a over c. So why does this all work? Well, what I'm doing here is I'm taking this triangle and I'm redrawing it right here with the hypotenuse c. Now let's redraw the same triangle with the angle theta with hypotenuse 1. The important point here is that these two triangles are similar because the three angles have to add up to 180, and since two angles are already the same, that would mean that these angles are also equal. So these are similar triangles. Now this leg here would be cosine of theta because we are on the unit circle, and over here, this leg, this side is a. Right, I'm just redrawing this triangle up here where that adjacent leg has length a. And then since I'm on the unit circle, the x-coordinate to the point on the unit circle is equal to cosine theta. Now, back to high school geometry and what you learned about similar triangles. We know that cosine of theta over 1 is equal to a over c. Right, that's because a and c are corresponding parts, corresponding legs in the similarity, and c and 1 are corresponding hypotenuses, the corresponding sides in the similarity. So this is to that as this is to that. There we go. So guess what? Cosine theta is equal to a over c. That's right here. Cosine of theta is adjacent over the hypotenuse, a over c. Let's take a look at what's called the complementary angle theorem. Let's look at this triangle right here. In this case, B and A are complementary angles. That means that their sum is equal to 90. Remember, the angle sum in a triangle is 180. This one is 90 of it, so that means A plus B have to equal 90. So these are called complementary angles. Now let's look at the sides of length A and B and the relationship to the two angles A and B. Notice that this side here, A, is adjacent to the angle B, whereas this side here is opposite the angle A, right? So A is adjacent to B, there, and A is opposite of big A. In a similar way, this side of length B, well, that's opposite this angle B, right? Opposite of B. And this side of length B is adjacent to the angle A. Okay, so now back to this part right here. So let's see here, looking at sine of B, the sine is the opposite over the hypotenuse. So the sine of B, okay, over here, here's B, opposite is little b over the hypotenuse C, right? So the sine of B is little b over little c. Likewise, the cosine is the adjacent over the hypotenuse. Now, we're talking about the cosine of A. So here's A. The adjacent side is B. So adjacent over hypotenuse is B over C. Look, sine of big B equals the cosine of big A. That's the complementary angle theorem, because big A and big B are complementary angles, and so their sines and cosines are the same. So for example, the sine of 30 degrees would be the same as the cosine of 60 degrees. 30 and 60 are complementary angles. Sine and cosine are cofunctions. Here's another example. 40 and 50 are complementary angles because they add to 90. Tan and cotan are cofunctions. You can see the complementary angle theorem in play back in that old table of trig functions that I showed in the previous video. Let's look at the sine of 14.5 degrees. So 30 minutes is 30 over 60. So 30 minutes is half a degree. So sine of 14.5 degrees is a sine of 14 degrees, 30 minutes. Now if I look down here, sine 14 degrees, 30 minutes, that looks like 0.241038. Actually, I mean 0.25038. Now the coangle to 14 degrees 30 minutes is 75 degrees 30 minutes. Right, 75.5 and 14.5 add up to 90 coangles. Therefore, the cosine of 75 degrees 30 minutes is found right here, and that's of course the number I just looked up when I did the sine of 14 degrees 30 minutes. Coangles 75.5 plus 14.5 is 90. Sine and cosine are cofunctions, so they have the same value. Notice the way this table is organized. Up here we have functions, sine, tangent, cotangent, cosine. And down here we have the cofunctions, right? Sine and cosine, tan and cotan, tan and cotan. And so, therefore, you can see the complementary angle theorem in this table.